So we found the emissivity from Bremsstrahlung, right? It is a constant plateau, and then you have a thermal cutoff. So let's recall Kirchhoff's first law that says that the emissivity is the opacity times the Planck function. So the intensity is the Planck function in Kirchhoff's first law. And that is the source function, that is the emissivity over the opacity. So if you write that opacity is equal to the emissivity over the Planck function, and multiply both sides by the density, and I'll substitute the Bremsstrahlung emissivity into this. This is the expression that you obtain for kappa rho. Now consider the Rayleigh-Jeans tail of the distribution. That means when the energy of the photon is much less than the thermal energy. So then you get rid of this exponential, and you have then, instead of 1 minus this exponential, you have h nu over kt. Then that is the expression that you obtain. Now this expression is very important. It tells you that the opacity has a dependency of 1 over frequency squared. That means that the intensity, which is the emissivity over the opacity, and because the emissivity is flat, the intensity is going to have a tail that is increasing with the square of the frequency because of absorption. So the intensity is going to have an exponential cutoff in emission at high frequencies, but it's also going to have a tail at low frequencies that goes with the square of the frequency. This is the emissivity. This is in log scale, so you have it in the flat, plateau, and then the exponential decay. The opacity, though, is falling as 1 over nu squared. So you have the parabolic fall here of the opacity. If you compute the optical depth, this is the optical depth. You see that at some point here, as you go to lower frequencies, it becomes optically thick because the opacity is very high at low frequencies. When you have the optically thin case, the intensity is given only by the emissivity, so then you have the Bremsstrahlung. But as you go to optically thick, you have to take the opacity into account. And that's when you start to have the Rayleigh-Jeans tail. The three conspicuous features of thermal Bremsstrahlung are the plateau of constant intensity, that's for the optically thin emission. You have the thermal cutoff, because the electron cannot emit a photon of higher energy than its kinetic energy. And you have this new feature, this third feature, which is the self-absorption at low frequencies when you have that the spectrum is optically thick. This self-absorption is the Rayleigh-Jean tail of intensity proportional to the squared frequency. Now you can imagine what is going to start to happen as you increase the density, as you start to make the spectrum more and more optically thick. As the medium gets optically thicker, the self-absorption starts to eat away the constant intensity plateau, the flat part of the spectrum, the optically thin part of the spectrum. So the Bremsstrahlung starts to become more and more like a black body. These are curves of different density. As you go increasing the density, the optically thin plateau becomes smaller and smaller. And then eventually the whole spectrum becomes self-absorbed, and that's the black body curve. As one increases the density, one increases the optical depth. And when the whole spectrum is optically thick, the whole spectrum becomes self-absorbed, and Bremsstrahlung becomes black body. Note that the Bremsstrahlung depends on the density, but the black body does not. This is because, again, the spectrum is optically thick. So you receive radiation from only the last mean free path. And the absorption decreases as the density increases, but so does the emissivity.